Yeah, so we learned Green's theorem. There are two versions. So what was that? Yeah, so if you have a two-dimensional, yeah, yeah, if you have a two-dimensional vector, yeah, this is two-dimensional. So this is what happened to my pen. Wait a second. Yeah, if you have a two-dimensional vector field, yeah, so this is a two-dimensional vector field. Yeah, and with the domain, so this is this is my domain D, and I have a vector space, vector field. So remember at the beginning I said to you we are studying about vector fields, right? So this is a vector field. Now we consider curve in this simply connected domain. D is simply connected. Now we computed, so let's say this region, yeah, so we, this is positive oriented, that is very important. And so first theorem says, we measured the tendency of this vector field to be aligned to the tangent to the curve. So everywhere dispersing this, spreading this vector field everywhere. But tangent vector is this one. I will write different color. Draw that in different colors. So this is the tangent. You always consider the component of this. So you just take the cos, dot product, and take the component of this vector field. Always component. Yeah, this is the tangent. Take the tangent component and take the tangent component to this, like that. So you measured the tendency for the vector field to be aligned with the tangent to the curve, so which was given by this. So this is positive oriented, this side, right? Which is given by f dotted with dr. So which is using the Green's theorem. So we don't need to evaluate this line integral. Instead of evaluating this line integral, we can find this double integral over this region. Let's say this region is R. This would be the curl of f, and kth component of curl of f. But you have to consider kth component. The circulation density times dA. dA is a infinitesimal area part in region R. This one. So this is the, I would like to, second. This is the Green's, the first version of Green's theorem. And the other version, we measure the tendency of the vector field to be aligned with normal vector to the curve, normal vector. So this time, so this time f dotted normal vector let me go to the second version. ADS. Okay. Okay. I will use this notation. Yeah, that is very clear. So this is a tangential component. First one. Yes. Measure the tendency the vector field to be aligned with the tangential, which is the first version, and the second version, the vector field aligned to be normal. Yes. Yeah, which is the divergence. Divergence over the region R. Yep. So I will put R here, this region. If you label this D, use D then, right? Okay, this is the two-dimensional version of a circular, the vector field to be aligned with, vector field to be aligned with the tangential to the curve, and align with the field to be aligned with normal to the curve. Okay, so this is the two-dimensional version, right? So green talked about two-dimensional domains. Yeah, so this region is a subset of a two-dimensional space. Now, what if you have a geometry, let's say three-dimensional geometry, right? A surface. So this is like this. The asbestos. Yeah, sheet. Yeah, this is a sheet in three-dimensional space. Now you have a vector field. This vector field is a three-dimensional vector field. Right? And now we are, so consider, let's say this boundary. So this is the boundary of this surface. C. It has a positive oriented boundary C. Okay. And here we have three-dimensional. Now we have three-dimensional vector space. No, vector field, sorry. So this is a two-dimensional greens. This is greens one is two-dimensional vector field. Now our geometry embedded in three-dimensional space, right? So this is a three-dimensional object in three-dimensional space. Now you have, let's say this is the wind velocity. Yeah, it is a three-dimensional vector field. Yeah, wind velocity vector field. Yeah. So now, so here you have geometry. Let's say this is your a part of roof, right? A sheet part, right? A part of roof, right? So now you want to measure the tendency for the vector field, velocity field to be aligned with the tangential, which is let me check the so Stoke tangential. So this is your three-dimensional surface and positive oriented, right? Positive oriented So positive oriented induces positive oriented of a boundary C. Then this one is positive oriented. Right? Yes, all right, surface. Okay. And this is your, let's say this is your three-dimensional field. Yeah. So this is your field, spreading everywhere. And this is normal to the surface. This is the normal vector to the surface, right? Okay. All right. So SP, the oriented piecewise, piecewise. Okay. Then the tangential, yeah. Then the tangential, yeah. So then the tendency for the vector field to be aligned with the tangential vector to the curve. That means the 3D version of this. So this is the 2D version of Green's theorem. 3D version would be, same thing, right? Now you get, which is called Stokes theorem. So you find, the tendency, you measure the tendency for the vector field to be aligned to the tangential vector to this boundary, right? So which is same with so circular so this is the circular density curl, so curl double integral over this, let's say this is the region R, curl of F times this is A, so this A, so this time A, curl of A Stokes dotted curl of A dot ds this d, I will call this is your sigma plane, right? Sigma surface, three-dimensional surface. This is your, I stick to previous notations, right? So this is sigma. This sigma is your three-dimensional surface, right? Okay. So this sigma can be written in terms of two variables, u and v, right? Sigma can be written in terms of two variables, right? And this is embedded in three-dimensional space. Okay, and I will consider an infinitesimal area part on this surface d sigma, and actually which is so let's say this is n, so, or you can consider this vector, dotted d sigma, which is same with n dot d sigma, scalar d sigma. All right, this is the Stokes theorem. Same thing here. Here you have kth component of curl of f, right? Circular density. Now in general, look at this. So curl, circular density throughout this entire surface. So this is called Stokes theorem. Stokes theorem. So according to our notations, I will stick to our notation. This is our sigma plane, big sigma, and this is your small d, small sigma. And if you write this one, you can write this one with vector. So this is so this is normal vector, unit normal vector. You can write the vector sigma in this way, unit normal vector times d sigma, right? So this should be sigma, and according to our notation, the sigma vector. Okay, so this is called Stokes theorem, right? I will answer kth component. What is kth component? In two-dimensional version of, so this is the Green's Green's theorem, first version of Green's theorem. Kth component, this is the unit vector alone or z-axis, right? So now we, so this is the three-dimensional version of, so we extend this Green's theorem to the three-dimensional, for a three-dimensional surface. Yeah, earlier our one was, this one was a two-dimensional surface, right? So now this is embedded in two-dimensional space. So this surface this surface is embedded in three-dimensional space. Okay, so this is the 3D version of Green's first version. So this is the two-dimensional version, and this is the three-dimensional version. Okay, and what does measure using Stokes theorem? No, we also use we also compute the circulation of the vector field. We measure the circulation of this vector field. Or if your particle moving along this one, we measure the work done on the particle, right? We measure the circulation, but using these theorems, this can be computed very easily. You can compute this one, this line integral for closed curve, but if you have these identities, you can compute this integral easily. All right, so this is the Green's first version of Green's theorem. Now we generalize that first version of Green's theorem. So which is this one. This is the 3D version of Green's theorem. So this is the 3D which is called Stokes theorem, right? So same integral, you get the same integral. So now your boundary is this one. This is your boundary. So C is a curve in three-dimensional space. So earlier this is your C, which is a this is a curve in two-dimensional space. Got it? So far so good, or do you have any questions? This is two-dimensional one, Green's theorem, and this is Stokes theorem is the three-dimensional one. Got it? Did you understand that? Let's see. So now this is two-dimensional one. So we have a region in two dimension, right? So now we have a surface. So this is your surface in three-dimensional space. Like this is your asbestos sheet, right? Right, and this is your three-dimensional vector field, like velocity of wind, right? So which is a three-dimensional vector field, right? Okay, Now we want to measure the tendency for this vector field to be aligned with the tangential vector to this boundary. So how do you compute that tendency for the vector field to be aligned with the tangential vector to the boundary? So for that we use so which is this one, which is this one. But if you apply Stokes theorem, you can obtain this value from this double integral very easily. Sometimes it is easy, sometimes it is hard, sometimes this can be evaluated easily, sometimes this can be evaluated easily than this method, this one. To compute that line integral, we can use this we can evaluate this double integral. Got it? So this is the three-dimensional. So this one is the three-dimensional version of Green's theorem, and Green has another version. So this is the two-dimensional. So this is the flux version. Remember, right? So Green has two versions. Flux form. So it measures what is the tendency, or we measure the tendency for the vector field to be aligned with the this time normal vector to the curve here. So these are the normal vector. කොහොමද මේ අපේ field එක මේ two dimensional field එක මේකත් එක්ක කොච්චර align වෙනවද මේක වටා මේ වක්‍රය වටා යනවා. අන්න ඒක තමයි measure කරන්නේ මේකෙන්. ඒකම තමයි මේක. Green's theorem, okay? If you generalize this concept for a surface like this, you can do that. So which is this one is same with this is two-dimensional one, 2D. Now the field is 2D. Now we consider a surface. So this is sigma surface, and your vector field also three dimensions, right? This one 3 dimension, and your curve boundary is also in 3-dimensional space. So how do you use so this is called divergence theorem. This is same with this is same with this is double for 2-dimension, 3-dimensional, triple integrals. So same divergence at a point. Locally, we add local properties to get global property of this global property of this surface over this surface. Add up all local property dot divergence throughout this time throughout you have I think for to use divergence theorem. The surface should be closed, I think. Sigma and a solid, right. If you have a solid, so let's see, S is a solid like this, and S is the bound. No, so you have a sigma is the surface in R3, R3 which bounds a solid S. Okay, so this is a solid now, right? Solid, 3-dimensional solid, like a ball, like this shape. So this is a solid. So leather ball, and surface is the S, right? Surface is the S, okay? S is the boundary of which bounds a solid S. Aha, let be the surface of R3 which okay, S is the solid and this is the surface of surface of this solid, right? Sigma is the surface, right? And if you have a three-dimensional vector space, vector field defined on R, so that contains sigma, then the three-dimensional version, so this means okay, surface integral, surface integral, so that means flux across this surface is equal to this triple integral. You add all divergence, or you add flux locally, you add up flux at locally, at a point throughout this entire volume. So this is a solid. S is the solid. This is the surface of this solid. Sigma is the surface, and S is this entire solid, right? All right. S is the solid, and the volume of this solid is, let's say, V. So this is the solid, and this is the surface boundary of the solid, right? Which bounds solid S. S is the solid. Sigma is the boundary of the solid. So the flux across this boundary is equal to this triple integral. Yeah, same thing here. So this time, not this one. Double integral f dot d sigma. Yeah, this is the connection. Yeah, so two-dimensional case. So this is the Green's. For two-dimensional case, you can generalize this case to three-dimension, right? So you get so same in line integral. Same line integral can be obtained for these kind of surfaces, three-dimensional surfaces. Now, for divergence theorem, you have a solid. S is this entire solid, and the boundary is the sigma, right? Sometimes we also get confused, right? Sigma is the boundary, solid is S, right? Okay, so the flux across this flux, here you have vector field, right? Vector field everywhere, spreading everywhere. So now we want to compute the flux across this boundary. So we want to compute flux across this boundary, which is this one, flux across boundary, which is same with add up all local so density. So this is the flux density. You add up throughout entire solid. Got it? So let's discuss couple of questions. Did you understand? Yep. So this is the last bit. These are the applications, surface integral of velocity, vector field. So first one, electric flux. So if E is the electric field, I want to find here flux, electric flux of this vector field throughout this surface. So කොච්චර කැපෙනවද මගේ surface එක electric field එකක් තිබ්බොත් ඒක කොච්චර කැපෙනවද ලම්බකව කැපෙනවද මට බලන්න ඕනේ ඒක measure කරලා. එතකොට තමයි මට ඉලෙක්ට්‍රික් ෆීල්ඩ් මොකක් හරි ප්‍රයෝජනයක් ගන්න පුළුවන් නේ. ඒක තමයි flux, electric flux of electric field. right? ලම්බකව හැමතිස්සෙම ලම්බකව සමහර විට සර්කියුලර් එකත් කැල්කියුලේට් කරනවා. මේක මතකනේ දෙකක් තියෙනවා. සර්කියුලර් කියන්නේ මගේ ඉලෙක්ට්‍රික් ෆීල්ඩ් එක කොච්චර මේකට සමාන්තර වෙනවද ඒක කම්පියුට් කරනවා. අනිත් එක ලම්බක වෙනවද මේ මෙහෙම එකක් තිබ්බොත් කොච්චර ලම්බක වෙනවද. ඒ ජියෝමෙට්‍රිය සර්ෆස් එකක් නම් ඒ සර්ෆස් එකට කොච්චර ලම්බක වෙනවද මගේ මේ වෙක්ටර් ෆීල්ඩ් එක කොච්චරක්ද ඒක කම්පියුට් කරන්න. මේක හරහා කොච්චරක් ලම්බක වෙනවද කොච්චර ප්‍රමාණයක් අන්න ඒකයි කම්පියුට් කරන්න. Can we compute the alignment of vector field to the surface using surface? Yeah, surface integral. Yep. So from the surface integral, we compute the same thing. But using these theorems, we can easily evaluate that. So using this identity, without computing the surface integral, you could compute this one very easy. Let's see. So here, so this is one of so this is divergence. Yep. So you have let's say this is your solid and boundary of that solid is sigma, and you have a magnetic field. Let's say you have a vector field. Let's say electric field, your electric field, right? So I'm going to compute how much my field across this surface, right? So which is this one? So which is this? I want to compute this one. So instead of computing this, I can use this identity to compute that, right? So this is the divergence theorem, right? Okay, let's compute. Okay, evaluate this here. Evaluate the surface integral. This is the surface integral. What is your field? Field is 1, 2, 3. It is a three-dimensional vector field, and sigma is the unit. Okay, solid is the solid sphere, centered at the origin, and the radius of this sphere is 1. Centered at the origin. So this is my geometry. Let me draw the geometry. So you know X, Y, and Z, and I place a geometry at the origin. So centered at the origin and with the radius 1, and you have a solid ball like a leather ball, not hollow, very solid ball. And the surface of this ball is sigma. Sigma is this the surface of this solid, right? Got it? Right. So I have a field, electric field, okay, going everywhere. So electric field going everywhere. I want to compute how much my electric field across this boundary sigma. So let's compute. So to evaluate this one, I will use divergence theorem. Which is this. This is same with triple integral over this solid. Let's say your solid is S, and you add up all local properties. I compute flux density at point and sum up throughout this geometry, three-dimensional solid. So compute this dV throughout the I will say V. So entire domain. So entire solid. So this is a infinitesimal how do you say this? So one of size is dx, dy height is dz, right? dv is the infinitesimal volume dx, dy, this kind of cube, yep. dx, dy, dz. Okay. All right. So this is dv. Let's find, yeah. So yeah, divergence of f. Okay, let's find that. So this is from the divergence theorem, this identity, right? I use divergence theorem to compute this surface integral, right? So gradient, yeah, this dotted with f. F is this one very easy to find, which is 1 plus 1 plus 1. Okay, partial respect to x, partial y, this operator gradient dotted with your function x, y, z. Yeah, this one, this 1, 1, yeah, 1 plus 1, 3. Yeah, so this is 3, very easy. It is a constant. So what is the, so you take the triple integral, you add up all these things, these volume, infinitesimal volumes throughout the entire solid. So what is the volume of this solid, of a sphere? What is the volume of a sphere? 3 times that. So 3 times, so this is a constant 3. Yeah, 3 times triple integral throughout this volume. So this gives you the volume of a sphere. What is that? Do you remember? We can use that. Yeah. What is the volume of a sphere? Yeah, that's right. So instead of computing this double integral, why don't you use, yeah, so why don't you use divergence theorem to compute this? So this is the flux across the surface, which is same with this triple integral. So to compute that, so this could be a tedious job, right, for this geometry. But if you apply this divergence theorem, you could, yeah, very easily come, because this is a constant. Yeah, you can take it out. So because it is equal to this 3, constant 3. Yeah, so therefore 3 times the volume of a ball or sphere, which is, I don't remember, 4 over 3 pi r is equal to 1 r cube, I think. Yeah, 4 pi. So using, that's why if you use these theorems, very easy to find this double integral. Sometimes, right? Sometimes very easy to find. And if you use this identity, you could, yeah, easily find this line integral. Okay, right? So at the beginning, yeah, question mentions using the Green's theorem, compute this yeah, line integral. Using the divergence theorem, find this double integral. Using the Stokes theorem, find this line integral. Got it? Okay, this is one of examples. You could find this double integral. So this double integral, yeah, this is for a surface. Yeah, if your surface is closed like this, so this is a closed surface. Yeah, you can, yeah, put this. Yeah, you can put this. Yeah, this means, yeah, closed surface. Yeah. So any questions for this? Yeah, this is another example application. So this time the temperature at a given point of a body, right? of some kind of three-dimensional body, right? So you are finding, heat flow. Heat flow is defined, so it is defined as this vector field. So this is the heat flow, right, throughout that body, right? So kappa, remember in A level, kappa is the conductivity constant. Conductivity constant kappa. Yeah. All right. So then find the rate of heat flow across this surface. Yeah, you have three-dimensional surface, let's say some surface. You know the vector field, you know the vector field of this heat flow, right? So this is the vector field. And now you have any geometry, right? Three-dimensional geometry with this is the S, right? S. And you find the rate of flow across this heat flow across this surface. So for that you have to add up all, so find this double integral. So this is another application. All right. So this is a one of notes downloaded from the internet. So here we compute the surface integral. So this is the scalar version. Here this is a scalar function f and yes, scalar version. So did you remember we got, so let's you remember, so let's conversion, scalar version. So this is scalar version, but sometimes we may get confused. I think better not uploading, I think, otherwise you get confused. But so compute the surface integral. So this is a scalar function and surface is given, which is unit circle, unit sphere. And I will so I will upload to look at these calculations, because you need a little bit practice. And let's look at, and you can find the total mass if you know the density. Density and center of mass, right? Again, scalar function here. Surface is defined, so this is your surface and scalar function. So they compute. So I will upload for your. You can work out these problems. So to get an idea. So if your surface is piecewise smooth, then you can compute piece by piece and sum that up. So again, scalar throughout this surface is like this here. So there are S1 is this curvy surface of the cylinder, and there's another surface, and there's another surface circle at the bottom. So if you want to compute the surface integral, you have to compute, so throughout S1, S2, S3, so here. So surface integral throughout S1 is the curvy surface, right? So when you compute surface integral throughout S1, you get this. And throughout S2 is the bottom one circle, and z coordinate is 0, then which is 0, and the surface integral throughout this surface S3, which is this plane, and they computed and add all together, then So very difficult to find a surface integral if you have a complicated geometry. But if you use if you use divergence, sometimes you may use a divergence theorem. What is this? These are applications. This is for vector valued function, surface integral of for vector valued function. So this time here, this is your vector. And find so today I'm going to solve a couple of questions. So how do you find surface integral for vector value, right? So here we go. This time field is vector, right? This is a vector. So earlier one was a scalar. Here this is a scalar field, right? And they define the geometry. This is the geometry. For each surfaces, we have to compute this surface integral, right? And add up together at the end, right? Okay, so I will upload this one as well. So here we go. Find the flux of this field across the surface unit sphere. Unit sphere. Then you can parameterize your surface first. That is your first job. Using two parameters, u and v, right? Okay, or you can use any notation, right? And identify this this region variation of these two parameters, right? So this is a full sphere. So this is your angle. Let's say this is phi varies from 0 to pi. 0 to pi. And theta, this angle, we can rotate full circle. Okay, like that. And radius is 1. You are working on the surface. Unit sphere on the surface. Radius rho is 1. Like that. Geometry you can for the given geometry. So these are famous geometry. Sphere, cylinder, a part of a plane. So we could compute. Otherwise, you have to use computer to compute the double integral, surface integral. So this is the field cross. This is the field. So we want to find the measure the field to be aligned with the normal vector to the surface. So here. So look at, let's see. Let's compute couple of this one. So let's compute. Okay, this one. So this is here. So they are given geometry, entire geometry. So S1 is the upper part with the bottom one is circular bottom. S2. So that is the S. Defined by them, right? So Fs defined, which is a closed surface. So you can go through and you can do up. So I will upload this up. Okay. Finally, so you have to add up surface integral throughout each surface. S1 and S1 application. Okay, let's cancel. All right. So any questions? All right, so let's evaluate this line integral over. So this is the line integral. So if you have a, let's say if you have a particle, you move along this curve. So what is the work done? So this is the vector field. This is the vector field. So what is the work done on of this vector field on this particle? Yeah, let's compute that. You can compute this line integral without using so you can just compute this line integral if you like, but this time I'm using Stokes theorem to evaluate this integral, right? Okay, yeah, so here could be evaluated directly. However, it is easier to use Stokes theorem. You can compute this integral very easily. Yeah, so do it as a homework, right? So compute this line integral dr. You can rearrange this dt. So compute this line integral throughout this path. Now I am using Stokes theorem to compute that. Let's see. So Stokes says this line integral is same with the double integral of adding up all local property. What is the local property? Yeah, curl of that field, and you have to add up this local property throughout this entire S. Double ds. Yeah. So this is the Stokes theorem. Okay, so this is the Stokes theorem. Okay, first of all, let's compute this bit. Yeah, you know this. Yeah, let's compute. I don't have space here. Yeah, yep. So here we go. So they compute curl because I want to find this bit here first. The partial x with respect to x, y, z, and put your field here. X component, y component, and z component, and simplify. You get k component. This is the curve. Okay. And what is my surface? Surface is this one. Yeah, this is same with. Yeah, this is same with surface integral started with the normal vector. Unit normal is much better. And ds is this infinitesimal. ds is this is ds, infinitesimal area part ds. Okay, now I use so all right, so let's find this normal vector, right? Normal vector. Yeah, so you know the equation, which is this. Yeah, equation of this plane is this one. Okay, so how do you find the normal vector? So you know, so so normal vector would be partial. So this is a constant, right? Constant, and there are no external, so 0. And partial of this with respect to x, which is 1, and partial of this with respect to z, which is 1. So this is the normal vector, unit normal. Let's find the unit normal by dividing its magnitude. Yeah, square root 2. So unit normal. Okay, we found this square root times 0, 1, 1. I don't have space to write. Okay, square 1, comma 1, comma 1. Okay, unit normal. We found unit normal. We found this guy. We know this guy. Yeah, let's take the dot product. Okay, taking the dot product. Where's that? Yeah, let's take the dot product. So yeah. No, this is two-dimensional version. Yeah, ds. Let's take the dot product of this. So f dot unit normal. Yes, f is this. F. So curl. Yeah, curl dotted with the unit normal. Curl is 0, 0, 1 dotted with unit normal 0, 1, 1. I will write this square root 1 over square root 2 here. Sorry. So this would be 1 over. I'm sorry. Curl is this one here. 1. So this one. 1 plus. Yeah, 1 plus 1 plus 2 y. So 1 plus 2y y divided by square root 2. So this is this bit. Yeah. So let's see. So we found this guy. And we have a conversion, right? ds can be written in terms of this guy here. Yeah, ds is so can be written. So remember, ds is magnitude of so you have to first write this surface in terms of two parameters. Let's write that r uv. So first component is x. I will use u. I will use y for u. V for y, and z equals 2 minus 2 minus y is this is v. So then so I have to find. So this is. Remember? Do you remember last time? So this is RU plus RV magnitude dA. dA is this infinite sum of dA. So this is the conversion. So find d partial of I with respect to u. Let's find RU which is with respect to u 1, 1, 0, 0. RV with respect to v 0, 1. 0, 1, negative 1. Take the cross product. I, J, K. This is 1, 0, 0, 0, 1, 1, 1, negative 1. So what is this? 0 times 0, 0. I component minus 1. Minus 1 would be 1. So other one Other one would be 1, right? 1, this one. Yeah, so can you use, wait a second, I will complete. So magnitude of this here, magnitude of this, which is square root 2. So magnitude of this one is square root 2. This bit this is the conversion. ds is equal to this guy square root 2 dA. Okay. So this is our method. I think they use a different method. I think. So stick to one of our methods. I think. So right. So here, look at the normal vector. 1 over square root 2. Okay. This one 1 plus 2y divided by square root 2. Because let's use this conversion. So let's write ds in terms of square root 2 here. So this is square root 2 dA, right? So you know that so this guy is 1 plus 2y divided by square root 2. Then this is same with double integral 1 plus 2y square root 2 cancels dA. So we get this same result here. Now you can use polar coordinate, write this one in terms of polar coordinate, then you can get this. Got it? A little bit work, I think. Okay, this is your field, okay? Right? So write down. So this is your field. So which is three-dimensional field, X, Y, and 2z. Let's do this together, right? And this is your surface, right? Z is equal, this is the geometry, x squared plus y squared, and z restricted to these two values. 1. Okay. Field is given, geometry is given, right? This is the geometry. Let's see what this geometry is. And find the double integral, or find the surface integral throughout. Let's say I will denote, I will label this geometry as sigma, right? So earlier we used sigma, not sigma. Yeah. Find the surface integral of this field. Evaluate this d sigma. So can use any notation. So small to represent the vector, right? So can you explain again? So 25. So here vector field is given, which is a three-dimensional vector field. This is your geometry, right? This is your three-dimensional object, and find this. So this is the surface integral. So this is the flux across the surface, sigma. So this is the flux of this vector field across this surface. Okay, let's find. Do this together, right? Okay, let's do this. Okay, first of all, we have to identify this, what this object is, right? So let's identify that. Yeah, let's draw a small diagram, right? X, Y, and Z. Yeah, Z is, so you can, Z, so you can use polar coordinates here. X is equal R cos theta, Y R sine theta, and you take X squared Y squared, which is R squared, which is Z squared, right? 2 pi, answer is 2 pi. Okay, let's see. 2 pi, or let's see. 2 pi. Let's see. Don't know whether I from here. Yep. So I think this is one of your spot test question. I think. Yep. So. Yep. So this is R. Yeah. So your Z, if it is R is a non-negative because it is non-negative. Z is R. So yeah. So the variation of variation between so the relation between Z and R is linear. So very easy. So like this, as R increases, Z also increases linearly. 4 pi. Okay, let's see. Yes, it will. Okay, right. So we know that this has a circular so because you are considering this R cos theta so you get this geometry. Okay, so this is a cone. This is a cone. So Z equals 0 and Z equals 1, and here you get, and this is the projection. So you get this surface, right? Cone of this curvy surface. So we don't consider this top one, right? It is not. So we only consider this curvy surface of the cone. All right, that is your surface. It has only one thing, but so here look at these things. These things has many surfaces. So as that, So you have to compute each and every surface integral. For instance, here how many surfaces are there? So this is flat surface 1, and this is curvy surface 2, and bottom surface 3. So you have to compute surface integral for those 3 surfaces, right? So here in the question they are talking about this curvy one only. So they haven't defined this this top. They haven't discussed that. Okay, this curvy one. All right, makes sense. All right. Did you? Yeah, is it clear to you? Curvy one is the surface. So they define. So we define our geometry. So we identified the geometry. Okay, this curvy one. So now vector space. Yeah, this is your vector field is spreading everywhere throughout this. Spreading everywhere. This is your vector field. Going everywhere. Anyway, we have to count how much this vector field spreading out throughout this surface. So this is our surface, not top one, right? This curvy one. Okay, let's compute. Got it? So far, so good. Right. So let's break this one into So first of all, this is your surface. Yep. This is your surface. Let's write your surface in terms of 2 variables, and because you are small babies, I will use u and v. Otherwise, I can use x and y very easily, right? So I use x. X is equal to u V is equal to V, no, Y is equal to V. And my Z coordinate would be U squared plus, yeah, squared. Or you can use polar coordinates. Let's use polar coordinate if you like. No, no, at the moment, no. You don't need to worry. Yeah, at the moment. You can use r and theta here. Or you can use r and theta. I will write that down. So it is confused. I will use rho. Otherwise, you confused with this rho. X coordinate rho cos theta, y coordinate rho sin theta. This is either yeah, you could use u and v or and theta. Yeah, I will. Yes. Which one do you want? Yeah, this one or that? Yeah. So let's use this. Yeah. Okay. So then to find the normal vector, so you know the conversion. So this is your sigma surface. So this is the projection of this surface, which is a circle, and this is a infinitesimal area on sigma surface, d sigma, and the corresponding area here, dA. And yeah, so you know the conversion between, you know this conversion, d sigma is equal to magnitude of r u cos r v. Yep, so dA. Yep. So let's compute this. Yep. I j k. So this is r u cos r v. Yep. Partial with respect to u 1 0 when you, oh my god, this is when you differentiate this, what is this? Yeah, so 1 over, yeah, so you get something. Yep. So what is the minus? I think. Yep. So we have something -1. Yep. So remember, yep. So this, simplify this. Yep. So I do remember that. So what is this? Minus u, right? Minus u. Minus u. Am I correct here or minus v? Okay. Is this correct? So when you simplify this, yep, this one times that plus u squared plus v squared. J, this one, so v u squared plus v squared. Another one. So what? And take the magnitude. Oh my god. Yeah, so let's take the magnitude. Magnitude. Yep. 1. This one squared. Yep. So yeah, this one squared with this one squared. 2 u squared plus v squared. Magnitude, and you get denominator, you get Yeah, you can cross this off. Finally, you get this. Got it? Is this correct? Don't know. I made a mistake. Yeah, you had to say. Yeah. So do this calculation with me, right? All right, we found this bit. Let's see what else. Okay, we know this conversion. So this is same with square root 2 dA. All right, 2 sigma. We found that part. And what else? Okay. Let's find the unit vector to the surface. Mhm. Yeah, z. Yep. So square root y squared minus z equals 0. So this is a function of this is a level curve, not curve surface. Y z. Okay. So how do you find the normal vector to this level surface? Find the gradient. Oh my God. So again, differentiation of this with respect to x. This guy, yeah, this guy is a big cap. So 2x minus x, I think. Minus y. Is this correct? I'm not sure. Negative y. And so this is the normal vector. Find the magnitude. Yeah, unit normal. Yeah, magnitude of this. Yeah, what is this? Again, square root 2, right? This one square, this one square, this one square. Sum that up. Square root. And yeah, so unit vector, unit normal. Unit normal to that surface. This guy. Oh, I don't like to write this. Like level students square plus y square plus yeah, without computing, I think you cannot understand. You have to practice. Yeah, you don't need to think any. Yep. So there are no thinking processes involved in this. Just computation. Yep. So you have to get experience by doing. Yeah, by finding these derivatives. Where did you get? Yeah, here we go. So this is your surface here. So surface is defined. So I took this variable to other side, then that becomes equal, that equals to 0, right? So this is a function of x, y, and z. So which is equal to 0. This is a level surface of this one of level surfaces, right? Got it? If you know the level surface, then you are able to find the normal vector by taking the gradient of this. Yeah, okay. This is the unit, normal to the surface of this geometry. Okay, we found the unit normal to this. We found the unit normal. So n hat. Okay, unit normal. Okay, we have all right. So now our vector field spreading everywhere. So we want to get the unit. We want to get the component of that vector field, unit normal component of that vector field, right? F dot n, unit normal, d scalar sigma. Okay. Okay, let's find this guy. Okay, so we want to find the a unit normal component of the field, because we are measuring the flux across this surface. All right, makes sense? Okay, let's find. We have field. Where's the field? This is field. Okay, let's compute that. So I know x. I know the field. What was our unit normal? Oh my God, this one. No, this one here. So this one times that. Oh, very difficult. Let me write the field here. Here, what is the field? What is the field? X, Y to Z. Okay, X, Y. Yeah, X, Y to Z. Yeah, so let's take the dot product. Yeah, so let takes so dot product. Yeah, this one times this x squared. That y squared. Then when you simplify that, yeah, when you simplify that, you get plus y squared. And this one times this negative. Yeah, this one times this x squared minus x squared, do this. Then negative is common, so simplify, and this one negative to z. Let's write this one in terms of u and v if you are interested. V x equal u, y equals v, z equal x squared, u squared plus v squared. Yeah, so negative. Am I correct here? Here I'm again -1. Is that correct? Let me check. Yeah, I think so. So here 3. Yeah, so to use, yeah, so I will put 3 here, -3. Yeah, so I wrote this guy in terms of our two parameters. Now I have, let's see, let's go to the okay, I wrote this guy in terms of u and v. This derivative square root. Yeah, I think, yeah, derivative of square root. Yep, so yeah, so differentiation of this, differentiation of x half. Yeah, I think, yep, x. So n x n minus 1. Oh my God. Is that correct? Oh my God, negative. I put negative, right? I think I'm in that. I put negative, right? I made a mistake, right? There. So 1/2, 1 over square root 2. So square root x. So why I put negative there? Shit. So you should tell told me earlier. Where's that? Yeah, this I think you can. It's that I put negative there. So here, right? This should be positive, right? Is that right? This should be positive. Yes. Yes. Right. Yeah, this should be positive. Yeah, I made a mistake. Then yeah, this should be positive. Then it is positive. Then what happened to? Yeah. So this is just Let me check. F is this times this, right? Then, yeah, so x times x squared, then this is positive, and this is negative, and then this is what happened? And this is negative, right? Not 3, right? Negative. Is that correct? So this is negative x u squared plus v squared. All right. Well, thank you very much. Okay. So I have that bit. So negative u squared. So which is okay. Let's write. So here we have where's that? Where's my question? Yeah. So okay. Here we go. So this is negative x squared. What was that? I don't remember. So what was that? Yeah, negative this one. Let me write that. So this is sigma. Yeah, so let me rewrite this. Yeah, so this is T sigma. Yeah, so I have u squared plus v squared d sigma. All right, now we have the conversion, which is magnitude. So this one plus RV, yes, dA. So magnitude square root 2. Yeah, so this one. Yeah, so yeah, I could write that into here. So what happened to this? This is, do we have square root 2 in front? No. So when I take, so I forgot to put this square root 2 there. So here I should put square root 2, right? Correct? Yeah, square root 2. Here this, is that correct? Square root 2. So this should be, yep, so square root 2. All right. So this one times this, x squared over this guy, y squared over this guy. So you can simplify square root, numerator you have square root, yeah, x squared plus y squared minus 2 x squared plus y squared. So then minus 2 because of that, then minus. So this is minus, yeah, this one, right? So that goes with the square root 2, then finally, so we had to put square root 2 there. So this is square root 2, yeah, you can close this. Yeah, finally negative square v squared. So dA, yeah, you can use, yeah, so because look at the projection is a circular. You can write in polar coordinates. Yeah, use cos theta is other one, sin theta. Yeah, so this is dA is remember, yeah, dA d theta, yeah, d theta, and this one is d yep. So this is R again, d theta dr. Okay, so these two are independent, and let's put terminals 0 to pi. R varies from 0 to 1, right? 1. Got the geometry. Yeah. See, this is, I think, yeah, 1. Upper bound is 1. Yeah, 1. So 1, 1, and theta is independent. Yeah, you can this 2 here, 2 pi then. Another bit. Uh, 2 pi. Yeah. Yeah. I don't know. I got this one here. I hope, yeah, this